Now we'll start a new chapter, that is rigid body dynamics. We have done forces, we have done conservation laws, and now we are into rigid body dynamics. First of all, what do you understand by rigid body? What is rigid body? When do you call the body to be rigid? See, a body is said to be rigid if distance between any 2 points, on the rigid body doesn't change with time, or I can say does not change during the motion, right? Like, say this is the object, this is said to be rigid body. If I pick any 2 points on this, then distance between these 2 points, suppose I am picking this point, say it is P and Q, then this PQ won't be changing with time as the body moves, as the body is moving. It may be translating, it may be rotating. So this is called rigid body. This is a definition of rigid body, right? This is definition of rigid body. Till now what we have been studying was particle dynamics. We have been studying particle dynamics. I considered the rigid body to be a particle. I consider every body to be a particle, right? Because you know you have forces got two effects. When force acts on any body, then it has two effects. That is, one is translational effect and other is rotational effect. One is translational effect and other is rotational effect, right? So in translational effect, the point of application of force does not matter. I discussed this earlier also when I was discussing pseudo forces. Here in case of when you have, say you have a body like this, right? So in case of translational effect, say this is the body, whether you apply force over here or here or here or here, the acceleration which is produced is same. So it only depends on the magnitude and direction. The point of this translational effect, that is translational effect, is characterized by acceleration. It only depends on the direction, magnitude of the force and direction of application. It does not depend on the point of application. But in case of rotational effect, it does depend on point of application. It does depend on point of application. Like you have a sphere. If this is sphere, then whether you apply force over here or over here or over here, the rotation does get affected. It just not only depends on direction, magnitude, it also depends on point of application. Like if you apply force over here, the body may rotate like this. If you apply force over here, the body can rotate in opposite direction. If you apply force along the center, the body may not rotate also. When you are opening your door, the point of application does matter. You apply force on the periphery, on the other end. You don't apply the force on the axle, right? When you start your hand pump, when you operate your hand pump, you put the force on one end, right? You do not put the force on the piston. So whenever you are interested in rotational effect, the point of application does matter. Point of application does matter. So in that case, rotational effect does depend on point of application. So since it depends on point of application, force is not an enough quantity. Force is not an enough quantity. Force into itself contains the information about point of application. So force into itself as a vector quantity, it only contains the information about the magnitude and direction of force. It does not contain any information about the point of application. So here, when we want to study rotational effect, So first of all, I'll tell you, in case of rotational effect, I can't treat the body to be a point particle. I can't treat this sphere to be a point particle when I am trying to discuss rotation. Try to discuss rotational effect of the force. I can't treat the whole body as a point particle, because treating the body as a point particle kills all the information about the point of application. So here, treat any body as a rigid body, right? We treat the body as a rigid body. It has got a dimension, and dimension does play a role over here. So because point of application is very important over here. So the force is not an enough quantity. Force into itself does not contain any information on the point of application. So here we define a new term called torque. We define a new term called torque, which into itself contains the information, which incorporate into itself the information about the point of application. Torque developed by the force is given by, it's not a basic quantity, basic quantity is force itself, developed by a force F acting on rigid body is given by R cross F. It is R cross F. Torque developed by a force acting on a rigid body is R cross F. So if suppose you have a body like this and a force F is acting over here, this is force F acts, and you have, this is the point about which I want to consider a rotation, then I'll draw R vector over here. I'll draw R vector over here, and then your torque is defined as R cross F. We define torque about O. Torque developed by the force about point O is given by R cross F, where R is a vector from the point about which rotation is to be considered to the point of application of force, to the point of application of force, vector from point about which the rotation is to be considered to the point of application of the force, right? So this is R cross F. I can give you a short method of getting the torque. First of all, before that, let me discuss the direction. What is the direction of the torque? See, if when you want to find out direction of the torque, you join their tails. This is your R. This will be R. Just translate these vectors. This is your R, and this is your F. So, and in order to find out the direction of this torque, you put the fingers of right hand in the direction of R. You put the fingers of right hand in the direction of R. You put the fingers like this. You put your fingers of right hand in the direction of R. Put all the whole finger in the direction of R, and you curl your finger towards F. You curl your finger towards F, right? The thumb goes in which direction? Thumb goes in direction inward. So torque is inward. Inward torque denotes, inward torque leads, inward torque goes inward. The direction of torque is into the plane, right? So that's how you find the direction. When your torque is into the plane, it describes, it will lead to this kind of acceleration. See, it will lead to acceleration of this kind. The acceleration also goes inward, because this kind of rotation, see the direction of this rotation in clockwise direction, you can't see when the body is rotating in this direction. I can't draw a vector in this direction. Vector has to be straight. So I can't draw the vector in this direction. So what I do is, if I have to describe this rotation, I describe it by a vector which is going inward. If I want to describe this rotation, then I describe it by a vector which is going out. That is the direction of omega, right? If the body is rotating in this direction, the angular velocity is taken inward. If the body is rotating in this direction, the angular velocity is taken outward. You just curl. When a body is rotating in this direction, you curl the fingers of right hand in this direction. Thumb gives the direction of omega, right? If the body is accelerating in this direction, you just curl your finger in this. If omega in this direction is increasing, you just curl your finger in this direction. The thumb gives you direction of alpha, right? So the rotation, the direction of rotation, see, translation, I can just draw a vector in that direction. That will give me the direction of translation. But when body is rotating, I can't draw a vector in this direction. So what I can do is, I can describe this rotation by a vector in outward direction. You just curl your finger in this direction, the thumb comes outward. So this rotation is denoted by a vector in outward direction, and this rotation is denoted by a vector which is inward direction. So in this case, the rotation is, in this case, the torque is inward. Torque is inward means it will lead to this kind of acceleration. If the body is at rest, it will lead to this kind of motion in clockwise direction. That is what it means when we say torque is inward. It's not like body is moving inward, it is moving clockwise. Okay, so that's the meaning of the direction of the torque, or direction of the angular velocity, right? So we'll be following this kind of thing over here. The shorter way of finding F is, let me give you a short way of finding F. Torque, short way of finding torque. You just draw this line of force and take the perpendicular. Just draw the line of force and take the perpendicular from here, right? From the point of application, just draw and take this perpendicular over here. So this is the line, this is the perpendicular from the point of application to the line of force, and your torque, the magnitude I am talking only. The torque is just F into P. The torque is just F into P. And the direction, you understand, when you apply this force, it will lead to rotation in this direction. So the angular acceleration is inward. The acceleration is inward, right? So you can easily find the torque by just dropping a perpendicular from the point about which rotation is to be considered to the line of force, and just multiply the magnitude of force to this altitude P, right? This is all you can do. Even if you do this, you'll get the same answer. This torque is, the magnitude of torque is going to be, R into F, and this is the angle, so this is theta, so RF sine theta, and if so this is phi, like I say R into F into sine 180 degree minus phi, so that is RF sine phi, and R sine phi is nothing but P, right? So that's the magnitude. The easiest way is to drop a perpendicular from the point about which rotation is to be considered to the line of force, and just take the product of magnitude of force and the altitude, the perpendicular distance, right? I'll take a question to discuss this torque, how to find out the torque. I'll take a question. You have to calculate the total torque acting on the body shown in figure about point O, right? This is the body, rigid body given to you, and these are all the four forces acting on it, right? You have to find torque about point O. Let me call this as F1. This is F2, and this is F3. This is F4. Right. Now, torque developed due to F1 is going to be the length of perpendicular from the line of force to the point O, that is 4 centimeter, and 10. This is the magnitude. 10 into 0.04. So it's 0.4 Newton meter in clockwise direction. In clockwise direction, because this is going to move the body clockwise. This force is going to move the body clockwise. Torque developed by F2, you just produce them in this direction.
Okay, produce them in this direction, and this is a perpendicular. Okay, so perpendicular will be how much? This is 15 into 6 sine 37. 6 sine 37, and sine 37 is 3 by 5. So this will become 0.54. It is 0.06, right? It is 0.06. So it's becomes 0.54 Newton meter, and this force acting alone is going to move the body in anti-clockwise direction. So this is in anti-clockwise direction. Usually we take anti-clockwise direction as positive. Torque 3. This force is passing through the center. So R cross F is going to be, this is your R, this is your F, so they make an angle of 180 degree. And any force passing through the center is not going to produce any rotation, right? So torque is 0 in this case. And tau 4 is, you just produce this, just produce a line of force, and you just drop a perpendicular over here, and drop a perpendicular. So this is going to be 30 degree, 4 centimeters. So this is force into 4 centimeter into sine 30. So sine 30 is 1. So it is 0.4 Newton meter, and this force is going to rotate the body in this direction, anti-clockwise direction, right? So now the net torque is going to be, you just add the clockwise one and subtract this anti-clockwise. So it's minus of 0.4 plus 0.54 plus 0.4. So this is 0.54 in anti-clockwise direction. In anti-clockwise directions, this is a torque, 0.54 Newton meter in anti-clockwise direction, right? So this is how we find the torque.